Okay, welcome back. So this section, we're going to be starting our discussion of probability ideas. Right? We're kind of moving through this data analysis process. Right? That's where we collect our data in a good way, we organize our data, and then we want to analyze our data. Right? But to really be able to analyze our data using inferential statistics, right, they rely heavily on these ideas of probability. Okay, so we're going to be talking about these ideas of probability, and then we can move into inferential statistics. So this section, we're pretty much just going to be talking about some terminology, going through some notation, things like that, because that's really the first hurdle to get over in probability. We got to get all the words, the symbols, we got to get all that straight. All right. So what is probability itself? Well, it's a kind of a field in mathematics that you might define as simply just the study of randomness, right? Or an attempt to quantify random processes. And probability is a tool, just like algebra is a tool, or calculus is a tool, or geometry is a tool, kind of these subsets of math, right? And we use all of these, put them together with statistics. Okay, so that was more about what is the study of probability as a field, right? What a probability is, right? You might think of it as the chance of something happening, right? So we want to be able to interpret this chance. We want to be able to quantify this chance, right? And statistical inference is built on all these ideas of probability. So we said probability is the study of randomness. What is randomness? So kind of the idea of randomness is that we live in an unpredictable world, but sometimes we can nail things down enough to model them, some of these ideas of probability. And those kind of deterministic models, right, are based on long-term patterns. So this is more about how we want to think about probabilities, right? We don't want to think about probabilities as just some sort of short-term thing that we can use to predict single outcomes, right? We want to think about them as long-term patterns. And that's what this idea of the law of large numbers means to us, right? So basically what the law of large numbers says is the more I repeat a process, the closer my results should be to what I'm expecting. Okay, so for example, right, if I toss a coin, we know theoretically 50% of the time I should get heads, 50% of the time I should get tails. Right? But if I just toss a coin one time, there's no way I can predict what it's going to be. If I toss a coin twice, I should get one heads and one tails, but we don't know that that's going to happen for sure. If I toss it 10 times, I get 5 and 5 tails, right? But I could get 10 heads and no tails potentially. But as I start tossing a coin more and more, right, if I were, say, to toss a coin 1,000,000 times, I'd be willing to bet that I'd get pretty close to half heads and half tails. Okay, so probabilities need time to work themselves out. Right? That's why some situations lend themselves more to analysis, to probability, because probabilities have more time to manifest themselves. Right? Like in the sports world, some sports lend themselves better to analytics than others. Baseball lends itself really well to analytics, right? Because you have large sample sizes, you have time to work things out. Sports like maybe football, not so much, right? In the NFL, they only play a few games. It's a much more stochastic sport. Baseball is a much more deterministic sport. A lot of the basic examples that you'll see in probability are kind of these like gambling type examples, cards, dice, flipping coins, stuff like that, right? Because of course that's where a lot of these ideas originated from, right? A lot of these early mathematicians were thinking about some of these ideas, and rich people that wanted to do better at gambling would hire these mathematicians to figure out these patterns. How can they do better at gambling and things like that? So here's one of the first guys Cardano, he was Italian, that really started quantifying some of these gambling games like dice, cards, and really started coming up with these ideas for probability. So all of this to say, we really should think about probabilities not as short-term predictors, but more like long-term patterns. All right, so let's define a few things here. So our probability experiment is the process that we're repeating, that we're easily able to identify certain outcomes. Right? An outcome is a result of a probability experiment. Your sample space is the set of all possible outcomes. We may be able to list this sample space, we may not. Right? An event is what we're interested in. An event, it may just be a single outcome, or it may be a collection of those outcomes. Right? But the idea here is we're trying to move towards this thing called a probability model. Right? And that's where we're able to actually use some sort of probability-based mathematical model to model a situation, to model a scenario. Right? There's lots of different types of probability models. We use them all the time. We see them all the time. But in some way, shape, or form, they're going to list all of our possible outcomes and have a way of assigning each of those outcomes a probability. So how do we get there, or how do we actually find some probabilities? I think the first place we need to start is the axioms of probability. So we've really kind of defined already what a probability is. Okay, but the ground rules or the axioms of probability are, number one, that everything in our sample space needs to add up to 1. The probability of each outcome in our sample space always is going to add up to 1. Right. Our second axiom of probability, the probability of any event needs to be between 0 and 1. Okay, so we'll never have negative probabilities. Right? We'll never have probabilities greater than 1, but a probability of 0 means this is something that's impossible. Right? A probability of 1 means this is something that's certainly going to happen. Probability of 0.5, a coin toss, right there in the middle. Okay, our third axiom of probability, though, I have it in gray here because we don't really have the tools or the terminology in place yet to talk about the third axiom of probability, but we'll come back to that. Using those first two facts, we can find some probabilities, and some different ways we might do that are, number one, the classical approach. Right? This is the approach that I was kind of talking about with Renaissance era mathematicians. Okay, we could also use a relative frequency approach, subjective probability, and then we have more complicated rules when I've got maybe more than one event going on at a time. Okay, so the classical approach to probability is basically the idea that I'm going to picture or draw this sample space. I'm going to count my total outcomes. Like, for example, when we're rolling a dice, there's 6 ways that can turn out. Right? So each number on the dice has a 1 in 6 probability. So in general, my kind of thought process or my formula here is that I'm going to define my event, and then I'm going to figure out, okay, how many outcomes in that sample space are in event E. That's going to be my numerator. My denominator is going to be the total number of outcomes in that entire sample space. Okay, so this is when I'm typically dealing with equally likely outcomes. Right? So if I have n items in my sample space, the probability of each of those outcomes, if they're equally likely, will be 1 over n. Right? So this is for pretty simple situations. This is why things like cards, dice, stuff like that lends itself well to this classical approach. So the key to the classical approach is going to be defining our sample space and making sure we get a good count of our total outcomes. All right, we'll look at some examples of doing that in the future. Next, we want to talk about the relative frequency approach. All right, so whereas the classical approach was kind of a more theoretical thing, right, the relative frequency approach is maybe we're not able to define that sample space or think about the situation clearly. Right, well, maybe we can actually do the experiment and record what happens. Okay, so to at least estimate a probability, right? We can say, well, the number of times something happened in my experiment divided by the number of times I ran the experiment, right, should be a pretty good guess at that event's probability. So an example of something like that might be, well, maybe I roll a dice 12 times and I get a 3 twice. All right, so we would think that our probability then of getting a 3, I got it a 3 2 out of 12 times, or 1/6. All right, so that actually led me to the correct probability. There's also a chance, maybe when I rolled that dice 12 times, I only got a 4 once. Right? So if I was using the relative frequency approach, I would estimate the probability of getting a 4 as 1 in 12. But we know that's not necessarily true. Right? But what's something that could help make sure we get it right? Well, we could run this process more and more. Right? The more that goes back to our law of large numbers. Okay, so the last kind of approach to probability that some books mention is this idea of subjective probability. I'm not going to spend too much time here, but if I can't picture the sample space, if I can't actually run the experiment, sometimes I might just apply a probability to a situation based on my own understanding, if I have a good understanding of the situation. All right, but we don't want to go around guessing too much, so it's not a extremely precise way of doing things. We definitely can hear some echoes of that law of large numbers there. The more I do a process, my relative frequency approach should move towards those theoretical or classical probabilities, right? So I bring this up, but one interpretation of these probabilities, the law of large numbers people might have, is that if I see something happening over and over, right, then, for example, someone's on a winning streak, or a basketball player's on a hot streak hitting a bunch of shots, right, then it somehow changes the probability of the next outcome. And we don't want to interpret the law of large numbers that way. Right? The law of large numbers doesn't say if, like for example, I get a bunch of heads in a row, the next flip is more likely to come up tails. All right, that's false. Okay, streaks are actually kind of common. There's been some research into streaks and some interesting books written on that topic, but make sure you don't interpret streaks that way. Okay, another important concept that we need to talk about here is the complement. Okay, if I have an event and I say know the probability of that event, or I know the outcomes included in that event, the complement of that event is all outcomes in that sample space that are not included in that event. Okay? Alright, so let's continue to try to find some probabilities by defining this thing called the complement. Okay, so if I am able to picture my sample space, I know the outcomes contained in an event. The complement of an event are all of the outcomes that are in that sample space but not in that event. So for example, what if my event is rolling a die and getting a 4? Well, everything else in that sample space outside of a 4, that's a 1, 2, 3, 5, or 6. Right? If my event is picking a letter of the alphabet and getting a vowel, well, my complement is everything else in the alphabet, consonants. Right? If my event is picking a day a week and getting a weekday, right? Well, my complement then is going to be the weekend, Saturday or Sunday. Okay, so we can easily find these probabilities based on our axioms 1 and 2. So since our entire sample space adds up to 1, that means that this first way of writing the complement rule on top here, right, is that the probability of an event A plus the probability of its complement needs to add up to 1. All right, that makes sense. Then the next two ways of writing this rule essentially say if I know the probability of an event occurring, then the probability of it not occurring is 1 minus the probability it occurs. All right, so these are our complement rules. It's a very simple rule, That's why we introduce it first. It follows from those first two axioms of probability, right? But we're not often going to see this rule used just by itself. We'll see it used in conjunction with other rules to make our life a little bit easier. Moving on from probably our easiest rule, the complement rule. For more complicated rules, more complicated situations, typically the first thing I want to look at, what if I have multiple events going on? Okay, the first thing I want to look at or think about is what does the relationship between these two events look like? And there's two main relationship words that I'm looking for. Okay, the first is if I have two events, are they mutually exclusive? Okay, so this is a phrase or a word I'm sure you've heard of before. Now the fancy probability way and a little bit shorter way of saying mutually exclusive is disjoint. Okay, but two events that are mutually exclusive or disjoint are two events that share no common outcomes. They can't happen at the same time. Right? Maybe one prevents the other from happening, whatever it might be, but they're two events that cannot happen at the same time. Okay, so that's our first relationship word that we're interested in. Are these events mutually exclusive? The next relationship that we're interested in is, are these events independent of each other? So what does independent mean? Well, if two events are independent, this means they have no effect on each other. So knowing one occurs has no effect on the other. Okay, now one point of confusion that I see, that I hear from time to time, is sometimes people like to say, well, mutually exclusive and independent are somehow like the opposites of each other. Well, no, independent and dependent are the opposite of each other, right? But whether two events are independent or mutually exclusive, these two things have nothing to do with each other, actually. Right? They are mutually exclusive of each other, if you could think about it like that. Okay, remember the definitions. Two events that are mutually exclusive can't happen at the same time. Right? Two events that don't have an effect on each other could potentially happen at the same time, or two events that don't affect each other could happen at the same time, right? So these are two types of relationships that don't necessarily have implications on each other. All right, so when we're trying to figure out what's going on with multiple events, the relationship between those events are the first and most important things. The next thing I really got to look at is, well, what exactly is going on here? What sort of combination of these events am I looking for? Okay, and there's two combinations that I may be looking for. So the first way we might look to combine events, the first type of compound event I might look for is called a union. All right, so the union of two events is going to consist of all the outcomes that are in the first and second event, in event A or in event B. Right, and so notation wise, we denote a union with this little symbol U. Okay, so the union denoted with the U, the keyword there is OR. The other type of compound event I might look for is an intersection. This is when I want to know something like the probability of this and this happening at the same time. Okay, so these are going to be the outcomes that are in both A and B, the shared events between these two outcomes, the overlap, the intersection of these two events, right? The keyword there is and it's denoted with this little symbol, that upside down U. Okay, so union's easy to remember. It's or, the symbol is that U. Intersection, we're flipping that U upside down. Keyword there is and. Okay, so when I've got multiple things going on, the first thing I got to think about is, well, what does the relationship between these events look like? What implications does that have? We'll talk about that. And then, what am I looking for? How do I find these compound events? So we'll see rules where we do this. All right, but right now we're mainly just interested in defining some things. Okay, the last thing we need to define is conditional probability. Okay, sometimes if I know one event has occurred, it might change the probability of another occurring. That's the idea of conditional probability. So given another event has already occurred. How do I update my future probabilities? What effect is that going to have on another? So here's notation-wise how we read that. We read it as, so this probability of A and this bar B. And that means A given B. So if B has already happened, what implications does that have on it? Alright, and then just kind of a side note here, just note that conditional probability statements like this, A, what's the probability of A given B versus the probability of B given A, these are two different things. Conditional probability sign there is not mathematically what we would call commutative. Right? Unions and intersections are commutative. Conditional sign here is not commutative. Okay, so I think this about covers most of the basic definitions that we need to talk about. We'll look at applications of these in the future. But for now, thanks for tuning in, and we'll see you next time.